Alright, hello everyone. I hope you guys are doing good. So today I will be discussing the solutions to Codeforces Round 756. This was a Division 3 round which ended like an hour ago. And first of all, talking about the difficulty, it was yet again a very well balanced round. It was like one of those typical Div 3 rounds in which the problems were not that hard and the initial problems were really easy and the difficulty increased quite gradually. So yeah, nothing to complain about on that front. The round was very well balanced and somewhat similar to a normal Div 3 round, right? So yeah, today I will be discussing the first 7 problems starting from A to F. And yeah, so let's start with the first problem right away. So in this problem, we have been given with an integer n in the input. That integer might be odd or even. But what we want to do is we want to perform some number of operations, and in an operation what we can do is we can take a prefix of a certain length and just reverse that prefix, right? So yeah, we can do this operation as many times as we want, and finally we want n to be an even number, and we want to output what is the minimum number of these prefix reversing operations that we need to do such that we get an even number. Yeah, that's the problem. And the solution here is rather simple. So the main observation here is that a number is even or odd is determined only by its last digit, that is the rightmost digit. So first of all, if the number is already even, then the answer is going to be 0 because we don't need to perform any operations. Otherwise, let's look at the condition where the answer will be -1. That is, we can never make the number even by performing the prefix reversing operations. And the answer would be -1 when obviously there are no even digits. Like all the digits are odd. So if all the digits are odd, I cannot do any kind of operation so that the rightmost digit becomes even, right? So if all the digits are odd, then the answer is going to be -1. And if the number is already even, then the answer is going to be 0. The other two cases are when the answer will be 1 or 2. And it can be very easily proved that the answer will never exceed 2. And so what happens is that if the leftmost digit is odd, then what we can do is we can simply reverse the entire number. We are allowed to do that. We can choose a prefix of length which is equal to the length of n and simply reverse it. And so the first number becomes the last number, that is the leftmost digit becomes the rightmost digit. And since the leftmost digit was even, now the rightmost digit is even and the entire number itself becomes even, right? So yeah, the answer is going to be 1 if the leftmost digit is even. Otherwise, if there exists a even digit which is not the leftmost digit as well as the rightmost digit, the answer is going to be 2. And the proof for that is that first, if the lth digit is equal to an even digit, then we can just reverse the prefix of length L. And by doing that, the lth digit becomes the first digit, that is the leftmost digit. And now we can do the same operation of reversing the entire string. And that would bring the leftmost digit to the rightmost digit. And we will be done in 2 operations. So yeah, this actually completes the solution to problem A. There is no need to go in depth here. The only 4 cases to look at are if the number is already even, the answer is 0. If there is no even digit in the number, then the answer is going to be -1. If the leftmost digit is equal to an even number, then the answer is going to be 1. Otherwise, there exists an even digit which is not the first or the last digit. So then the answer will be 2 because we can first reverse the prefix of length L, where L is the index of the first even digit. And now the leftmost digit is even. And then we can reverse the entire string, right? So this is the solution for problem A. Let's have a look at the code. It's nothing special here. These are all the 4 cases. First is when the last digit is even, and the second is when the first digit is even, and the third is that I'm trying to find the first index of an even digit, and if I don't find it, the answer is going to be -1. Otherwise, the answer is just going to be 2. Great. So this completes the solution to problem A. Let's now have a look at problem B. Again, a really easy problem. Let's see what this problem has to say. So yeah, in this problem we have to create a team, and not one team, we have to create many number of teams. And what we have is we have A programmers and B mathematicians available to us, and we want to create as many teams as possible. And the rules for creating a team are that each team must consist of exactly 4 students, and it is not optimal to take all the 4 students as programmers or all the 4 students as mathematicians. So we need to have at least one mathematician and at least one programmer in every team. And finally, these are the only two conditions we need to tell what is the maximum number of teams that can be made. Right. So again, this is even easier than problem A. What we can simply do here is, obviously the answer will never exceed a plus b by 4. That is a very obvious thing. But the answer can also not be like smaller than a. I mean, the answer cannot be greater than a, because if the answer is greater than a, that means we are creating more than a teams, whereas we have only a programmers, and so we can't have at least one programmer in every team, right? And similarly, the answer has to be smaller than or equals to b, because if the answer is greater than b, then there will exist at least one team which will not have a mathematician. This is a simple claim using the pigeonhole principle. So the answer to this problem is going to be minimum of 3 terms. First term is a, the second term is b, and the third term is a plus b by 4. Right? So that is the complete solution to this problem. However, during the contest, what I did was I did some binary search. So the solution which I just told is like really easy, but let's look at the binary search solution in this code. That would make it rather more interesting. So first of all, I know that it is obviously possible to create 0 teams. So I initialize L with 0 in my binary search. And I know that it is impossible to create a large number of teams. And so I initialize R with 10 raised power 10. Then what I do is in my binary search, if I'm checking for mid, that is, I'm checking whether it is possible to have mid teams or not. The only conditions for mid to satisfy is that mid should be less than equals to a, and mid should be less than equals to b, and mid should be and 4 times mid should be less than equals to a plus b. I mean, it is like really not a very good thing to do here, because it was an O of 1 formula straight away. But yeah, the binary search might be interesting. So if I'm okay, then I do L is equals to mid. Otherwise, I do R is equals to mid. So this is a binary search solution to problem B. However, there is also a simple O of 1 solution, and let's write that down. So we have an O of 1 solution, which is that answer is equals to minimum of 3 terms. First is A, second is B, and third is A plus B by 4. Okay, so this completes the solution to problem B. Let's move on to the next one. Okay, so we have problem C, and this is a very involved problem statement. So let's just skip the statement, and I will explain on the go what exactly is happening. So what's happening is initially we have a sequence A, and what we are doing is first we look at the first and last element of the sequence A, and we pick the minimum out of them, right? If the first element is minimum, we pick it, or if the last element is minimum, we pick that, and then we remove the minimum element from A and insert it into an empty sequence P. Right? So this is what is going on. Maybe in the problem statement they are taking A as P and P as A, so I'll do the same. So initially I have a sequence P, which is a permutation from 1 to n, and then what I do is I look at its first and last element, and whichever is minimum, I pick that up from P and remove it from P. And if the leftmost element was minimum, I add that element to the left of A, and if the rightmost element was minimum, I add that to the right of A. Initially A is empty. Okay, so I repeat this process, and this process can be visualized using this example where n is equals to 4 and p is equals to 3, 1, 4, 2. Here initially the first element is 3 and the last element is 2, and so the minimum of them is just 2, and so I remove 2 from p and add it to A, to the right of A. Initially A is empty, so it doesn't really matter where I add it. Now I have 3 and 4, and the minimum of them is 3, so I pick up 3, remove it from P, and insert it to the left of A, so A becomes 3, 2. Then I have 1 and 4, so I pick up 1 and A becomes 1, 3, 2. And then I have 4, which is just 4. So here they have allowed us to put 4 anywhere to the left or to the right, since it is the last element, so it doesn't really make any sense to regard it as a left element or a right element. So I can have 4, 1, 3, 2 or 1, 3, 2, 4. Here they have considered 1, 3, 2, 4. Right? So this is how we are making A from P. Now the interesting thing is that we don't have to make A from P, we have to make P from A. So in the input we have been provided with the resulting array A, and we have to find out any of the possible P array, any of the array which was given to us in the beginning, that we did the operations and we converted it to A. right? So we have to restore the array P using which we got to the array A. And obviously here there are multiple solutions possible. So we have to output any one of the possible solutions. Okay, so let's see how to solve this problem now. Also, it is not the case that the answer will always exist. There are some properties that the sequence A has to satisfy for the answer to exist, right? Now, let's try to write down some observations. First of all, the first thing is that we are always picking the minimum element from the left and the right elements, right? So the moment we encounter n, we know that P is a permutation from 1 to n. So the maximum element in the permutation is obviously n. And the moment we encounter n, we are never going to pick that element, right? If n is the leftmost element or the rightmost element, as soon as we encounter n, that particular point is blocked, because since n is the maximum element, the other element is surely going to be less. So we are going to pick that and only that. And so the first observation is that the last element to be removed from P is going to be n. And yeah, this is for sure. So I know that the last element that I'm going to remove from P is going to be n, because every time I'm picking the minimum from the leftmost and the rightmost element, and the minimum can never be n until and unless it is the only element left, right? And also in the problem they have provided me that I am putting the last element to the left or to the right of the sequence A. It is my choice. And so the only condition that the array A needs to satisfy is that it's either its first or its last element has to be equal to n. So either first or last element of A has to be n, right? So yeah, and it turns out there is no other condition that the array A has to satisfy, and this is a very, very necessary condition, because I have already proved that the last element that I will remove from P is going to be n. And if the last element being removed from P is n, then the last element being added to A is also n. And I have the liberty to add n to either the left or the right of A. So either the first element or the last element of A has to be equal to n. Okay. And now my job is half done. I have determined whether an answer is possible or not. Now I also have to output the answer. And let's see how to build the answer. And the main thing that we can do is we can fix n to be either the first or last element of P. We can fix n to be the first or last element of P. And this is just a hit and trial solution. And if you try to do this, you will realize that it is always possible to create a permutation P if you fix n to be its first or last element. And in the contest, I fixed P to be the last element. So let's see what happens if I fixed n to be the last element of P. So I have fixed n here, which is the last element of P. And now all these elements are free. And now what happens is, if I fix n to be the last element of P, when I'm removing elements from P, what I'll realize is that initially I'm looking at the first and the last element and I'm taking the minimum of them. And since n is the last element, I will make use of the observation that I made in the beginning, that as soon as I encounter n, that particular end gets blocked. And since I have already encountered n, this right end simply gets blocked and all the elements are removed from the first end, from the leftmost end, in order. So what happens is, if we look at the first example, we have 1, 3, 2, 4 as A, and if I fix 4 to the end of it, then what happens is, if I fix this element as 4, and then what will happen is, let's say all these three elements are x, y, and z. So then I'm sure that x is smaller than 4. So I will remove x and put it in A. So my A will become x. And then what happens is, I will be at y and 4, and I know that y will be smaller than 4. So I will take it out and put it to the left of x. Similarly, finally I am at z and 4, and I know that again z will be smaller than 4 since this right end is blocked. So I will take it out and put it here. So what I notice is that every element to the left of A, to the left of 4, is just reversed, right? To the left of 4, I had x, y, z, and finally I am having z, y, x, right? So what I can do is I can just fix n to be the last element and reverse all the n minus 1 elements, and that is how I can get to the solution. You can check that out in this case as well. If I have 3, 2, 1, so if I have 3, 2, 1, then I'm fixing 3 to be the last element, and if I just ignore 3 from the test case, I will be left with 2 and 1, and then I will just reverse 2 and 1 and I will put them here. So my final answer is going to be 1, 2, 3, which is indeed correct, right? So here they have given another answer which is also correct, but 1, 2, 3 is also a totally valid answer, right? Okay, so this makes sense to everyone. So let's just have a look at the code and then we'll move on. Alright, so first of all, I'm checking if either a1 or an is equal to n. If none of that is the case, then I'll simply output -1. Otherwise, if a1 is equals to n, then the leftover array is from 2 to n. So what I'm doing is I'm creating 2 pointers, l and r, where l is 1 and r is n. If a1 is equals to n, then I'm doing l plus plus, because now my array is from 2 to n. And if an is equals to n, then I'm doing r minus minus, because now my array is from 1 to n minus n. And so finally my array is from L to R, which I have to consider, and I'm fixing the nth element in P to be n, and after that I'm just going through L and R and reversing the array basically. So I'm starting with n minus 1, and my answer of n minus 1 is going to be a of L. Similarly, my answer of n minus 2 is going to be a of L plus 1, so on and so forth. I just reverse all the elements and append it to the left of n. Right, I hope this makes sense. So it's time to move to the next problem, problem D. Alright, so now we are at problem D, and the thing about this problem is that it is actually easier than it looks. And I mean, during the contest also, it took me a lot of time to figure this out. I mean, let me just show you how much time it took me to solve this problem. So during the contest, I was thinking about various ways to solve this problem. As you can see, I solved C in 17 minutes, and then it took me like quite a lot of time, 45 minutes to solve problem D. Even though this problem deserves nothing more than 15 minutes. So it's really unfortunate, but anyways, the point is that this problem is easier than it looks, and let's see what the problem says. So we have a tree, and in the tree every node has a number associated with it, obviously, and I mean, I don't know why they have complicated the problem so much, but according to the problem, any number can be the root of the tree. That is, any node can be the root of the tree. Maybe this helps in actually formulating the problem, but anyways, any node here in the tree can be its root, and basically we have another permutation given to us, and that is a permutation of numbers from 1 to n, where n is the number of vertices in the tree, right? And after that, we have been provided with the entire tree structure in the form of ancestors, that is parents. So it is obviously enough for them to provide the parents of all the nodes. If we have the parents of all the nodes, we basically have the entire tree. So we don't have to worry about that. And yeah, they have provided us with the entire tree structure. And now what they want to do is they want us to assign weights to all the edges of the tree in such a way that if we look at the weights of all the elements in the permutation, then we get a sorted array. Let's see more clearly what they're trying to say. So what we have to do is we have to assign weights to every edge of the tree, such that if we create a distance array where distance of I is the distance of node I from the root, then if we look at the distance of all the elements in the permutation that we have been provided with in the input, then that distance array of the permutations is a sorted array. Formally, what they want us to do is, if dist of I is the distance of node I from root, then dist of pi should be strictly less than dist of pi plus 1, where p is the permutation provided to us in the input. I hope the problem is clear enough to everyone. Okay, so yeah, we have a tree and the tree can have an arbitrary root, and our task is to assign weights to all the edges of the tree such that the distance of all the elements in this permutation are sorted. Great. Okay, and also it is not the case that this answer always exists. We have to tell whether the answer exists or not. If the answer doesn't exist, then we have to output -1. Otherwise, we have to output the weights that we have assigned to all the edges. Okay, so let's see how to solve this problem. Okay, so first of all, we need to figure out when the answer will exist, right? So for that, we need to make some very important and easy observations. And the main observation here is that the distance of any node in the subtree of a node u will obviously be greater than the distance of u, right? So let me write it down. Dist of u will be greater than will be smaller than dist of v for any node v in the subtree of u. Like, it's pretty easy to understand because in the problem they have given us that all the distance values that we have to assign must be between 1 to 10 raised power 9 and they can't be 0. So I know that there is a unique path from every node to root. So while I'm going from node v to root, if the parent of v is u, then obviously distance of u will be smaller than distance of v, because the difference between their distances is the actual weight of the edge between u and v, right? So that is very easy to understand. For any node v in the subtree of u, the distance of v is surely going to be greater than the distance of u. But what I want is that in the permutation that I have been provided, the distance of pi is smaller than distance of pi minus pi plus 1 for all i's, right? So if I want that, I know that a node v is in the subtree of node u, so distance of v will be greater than distance of u, and that is only possible when v is to the right of u in the permutation p, right? So I have the necessary condition for the answer to exist, which is that the distance of so it is that the position of any node v in the subtree of u should be to the right of u in the permutation p. And this is fairly obvious because if a node is to the left of node u, then its distance is smaller than the distance of u. And if the distance of a node is smaller than the distance of u, then it can't be in the subtree of u, right? So if any node is in the subtree of u, then it has to be to the right of u in the permutation p. And obviously there is no other restriction in front of us, so this is the only condition that all the nodes have to satisfy in order for the answer to exist, right? And this property can easily be checked using a simple DFS. So what I'm going to do is I'm going to do a simple DFS and check what is basically the leftmost node in a subtree, and if the leftmost node in the subtree is to the left of my current node, then the answer will never exist, and otherwise the answer will always exist. Yeah, so I can find out this condition and check everything with a DFS. So we can find out the leftmost node in the subtree of u, I mean the leftmost node in P, whose position in P is leftmost in the subtree of u, and let it be min. So let it be min. So if min is smaller than the position of u, if min is smaller than position of u, then answer will never exist. And that is to say that the element which is at position min is to the left of u in the permutation P, and so the answer will never exist. And it turns out this is the only condition for the answer to exist, and yeah, it's pretty clear. And now comes the more challenging part, I mean the seemingly challenging part, to actually assign the distances, right? Yeah, so now we have to actually assign the distances. We have done 50% of the task. We have checked whether the answer is going to exist or not. If the answer doesn't exist, we can simply output -1. But if the answer exists, now we have to actually assign the distance values. So we have this permutation p1, p2, p3, pi -1, pi up till pn, right? And this is a permutation of length n, so it contains all the numbers from 1 to n, and we need to assign the distance. We need to assign the edge weight for the edge which connects p1 to its parent. Similarly, we need to assign an edge weight to the edge which connects p2 to its parent. Similarly, we have to assign a weight to the edge which connects pi to its parent, and so on and so forth for all of these values, right? So what we can do here is we can simply go from left to right in the permutation and try to assign weights to edges. And what I'm going to do is, my invariant is going to be, I'm going to iterate from left to right in P, and if I'm at position I, then my invariant is going to be that I have successfully assigned weights to edges in the prefix P1, P2 up till Pi -1, and also calculated dist of j for all j in the prefix 1 to I -1, where dist of I is nothing but the distance of I from the root, right? Yeah, so this is going to be my invariant. And if I have this invariant and I am at an index I, and I just assume that I have successfully assigned weights to all the edges in the prefix 1 to I -1, and I've also calculated successfully the distance value of all the nodes in the prefix of 1 to I -1, then you will realize that it is really easy to assign the weight to the edge which connects pi to its parent, right? Also, the invariant also has this condition that I have assigned it in such a way that like the distance of p1 is less than distance of p2 is less than so on and so forth up till distance of I -1, obviously, because this is what has been asked to me in the problem. So obviously this is how I'm going to do it. And now what happens is that I need to make sure that distance of I is greater than distance of I -1. So why not just make distance of I is equals to distance of I -1 plus 1? What's stopping us from doing that? We can simply do distance of I is equals to distance of I -1 plus 1. And it is actually easy to prove that this is a possible scenario, and that is because we are at this element I, and obviously we know that the parent of I has a smaller distance value, right? And if the parent of I has a smaller distance value, then it has to be to the left of I, which I have already proved that the parent of every element will be to the left of it. So I know that the parent is in this prefix of 1 to I -1, and for all the elements in 1 to I -1, I have calculated the distance values. So I know the distance of its parent, first of all, and its parent is also between 1 to I -1. So I know that the distance of the parent will be less than this value, distance of I -1 plus 1. Why? Because simply I know that the parent is in this prefix of P1 to Pi -1, and this prefix has already been sorted by me. So if the parent is here, then the distance of the parent can be at max dist of I -1. So it can never exceed dist of I -1 plus 1. So what I can do is I can simply do dist of I is equals to dist of I -1 plus 1. And then I can easily calculate the edge weight. Edge weight of the edge connecting Pi to parent of Pi will just be dist of Pi minus dist of parent of Pi, right? So using this, I have simply maintained my invariant. That is, I have assigned a value to the edge which is connecting Pi to its parent, and I have also assigned the distance to Pi. So yeah, I have successfully maintained this invariant, and finally I will have assigned a value to all the edges. and I will have all the distances with me, and I will have successfully maintained this condition that the distances are in strictly increasing order, right? So yeah, this is it for problem D. It's a seemingly hard problem, but it's actually not very hard. So let's just have a look at the code now. Right, here we are. So what I'm doing is, first of all, I'm doing a DFS to actually check whether an answer exists or not. And in the DFS, what I do is I find the minimum position of all the elements in the subtree of a tree. And if that minimum position is less than the position of my current node, then the answer is never going to exist. And I do OK is equals to false. So yeah, once I do the DFS, I just check if I'm OK or not. And if I am OK, what I do is I create a distance array and an answer vector, where ansec of I is the length of the edge which connects I to its parent. And obviously, yeah, one more thing is that it is always necessary that the root of the tree is the first element of the permutation, because otherwise it is not possible for the permutation to be sorted, because the distance of the root will be exactly 0. So it has to be the first element of the permutation for sure. Right. So distance of 1 will obviously be 0, and the answer vec of 1 will also be 0. And then what I do is distance of p of 2 is equals to 1, and I mean this line is basically unnecessary, so we can comment it out and do this loop from 2 to n. It doesn't really matter. So what I'm doing is the answer vector, the length of the edge of pi to its parent is going to be distance of pi minus 1 plus 1, which is going to be distance of pi, and from this I subtract the distance of its parent, right? So that will get me the answer vec of p of I, and then I will have to calculate distance of p of I, which will just be distance of parent of p of I plus answer vector of p of I. That is the distance of its parent plus the length of the edge. And finally, I will have the edge lengths of all the nodes, so I will be good. So that completes the solution to problem D. Let's move on to problem E now. So there are two problems, E1 and E2, but what I'm going to do is I'm going to consider both of them together. And a very strange thing which I noticed here is that problem E1 has been rated 1700, while problem E2 has been rated 2000, which is something that I really fail to understand. And another thing that I fail to understand here is that problem E1 has around 1.5k solves, whereas problem E2 just has 500 solves, which is very difficult to understand, because in my code I just had to change one line to go from E1 to E2. So a possible explanation for this could be that a lot of people solved E1 in a different manner, and so they didn't get the idea for E2. But what I did in the contest was I did E1 and E2 in a very, very similar fashion. So I will be discussing both of them together. All right. Again, this is another tree problem, and let's see what this problem has to say. So we have a tree with n. So basically we have a maze with n rooms and n minus 1 bidirectional corridors. So yeah, we have a tree, bidirectional tree, right? And we have Vlad, who is playing a game with k of his friends, right? And what happens is that Vlad starts from the root of the tree, that is the node 1, and his k friends are distributed throughout the tree. There is exactly one friend in every, there can be at most one friend in every node of the tree, and all of these k friends are distributed in certain nodes of the tree, right? And what happens in the game is that every person, including Vlad, in every second can move, and every one of them can move along the edge. That is, they can move from one node to another if both of them are connected directly by an edge. And Vlad or his friends can or cannot move. It's their choice completely, right? So in every second, either some of them decide to move, some of them don't decide to move, but everyone who decides to move will move through one edge, and it will go through a node connected to the current node by an edge directly, right? So this is what's going on here. And yeah, in the problem we have to ask is, what the problem asks us is that Vlad is going to win if he successfully is able to reach a leaf of the tree. right? The rules of the game state that Vlad will win if he successfully reaches the root of the tree without being caught by any of his friends. That's the problem here. So Vlad has to make moves and he has to safely reach the leaf of a tree. He has to reach the leaf of the tree without getting caught by any of its friends. And getting caught just means that one of his friends and Vlad are in the same node. If both of them are in the same node, then it means that Vlad got caught by one of his friends. And what we have to tell is whether it is possible for Vlad to reach the leaf successfully without getting caught by any of his friend. And if it is possible to do so, then we have to answer something else. Okay. Also, one more thing to note here is that the friends play optimally. So, the friends know what the plan of Vlad can be, and they will try to counter his plan at all times. So, basically, Vlad can win if and only if there is a guarantee he will win. And that is also what they have been asking us, that whether or not there is a guarantee that Vlad is going to win or not. Because if even if there is a single way during which Vlad will lose and there are all the other ways through which he will win, all the other friends are going to follow that way that will make Vlad lose. So Vlad will win if and only if there is no possible way for his friends to catch him, right? Yeah. So the first part of the question says that we have to tell whether or not it is possible for Vlad to win. That is, whether or not it is possible for him to start from the root and end at a leaf. And now, if it is possible, if it is guaranteed that he's gonna win, we have to answer something else. And that something else is that we need to tell what is the minimum number of friends that must remain in the maze so that they can always catch Vlad. I hope it's clear enough what they're trying to ask. And what they're trying to ask is that we need to tell what is the minimum number of friends that must remain in the maze so that it is guaranteed that Vlad is going to win the game, right? I mean, Vlad is going to lose the game. Okay. Yeah, that's the problem. So if Vlad is going to win the game, then obviously the answer is going to be -1 in the problem. And if Vlad can lose the game, like it is, there is one possibility that at least one possibility that Vlad is going to lose the game, then we have to tell what is the minimum number of friends out of the K friends that are essential, that are required to remain on the maze so that they make sure that Vlad does not win the game ever. Okay, so this is the problem. In problem E1, they only asked us whether or not it's possible for Vlad to win the game or not. And in problem E2, what they have asked us is that if it is impossible for Vlad to win the game, we need to tell the minimum number of friends that must remain in the maze. Okay, enough of explanation of the problem statement. Now let's try to solve the problem itself. First of all, the crucial observation is that Vlad will win once he reaches a leaf. In the problem, they haven't mentioned in a straightforward manner when Vlad is gonna win, right? Yeah, so what they have written here is that friends are placed in the maze and the friends will win if one of them meets Vlad in any room of the corridor before he wins. Okay. Yeah, so Vlad is gonna win whenever he reaches a leaf. Okay. And now another crucial observation is that since it is a tree which we are dealing with, I should really remove this dark mode so that we can see the tree clearly. I guess the tree was there in problem E1, so it is beneficial to open that. Yeah, so here we have a tree. Alright, so the crucial observation here would be that if we have a leaf, then since it is a tree, there is going to be a unique path from the leaf to the root, right? Let's say that we consider this leaf 4. So if Vlad has to reach leaf 4, then he has to first reach 7 from 1. Similarly, if he has to reach the leaf 5, he will have to first reach 2, then he will have to reach 7, and all of that he needs to do without getting caught. So essentially, Vlad will win if there is a leaf such that it can be reached without ever getting caught. Okay. So my problem will be solved if I can find a way to confirm that there exists a leaf such that I can reach that leaf and all of its ancestors also without getting caught, because all of its ancestors will be in the path from the leaf to the root. So I have to go from the root to all of the ancestors of the leaf, and all of this I have to do without getting caught, and finally I have to reach the leaf as well. Okay, so the only problem left with me now to answer is that how can I actually check whether it is possible or not to reach a particular node without getting caught. If I can find a way to check whether it is possible or not to reach a node without getting caught, then I can simply start from all the leaves and check whether it is possible for us to reach all the ancestors of that leaf as well as that leaf starting from the root. So the only question left is for us to somehow check whether it is possible to reach a node from the root. And if we actually find a way to do that, we just have to find out a leaf through which it is possible to reach the root. Okay, so now again it is not very difficult to see how we can check that. Let's say that all the nodes which have a friend are red in color, right? So in the problem you can see all these nodes are red. These are the nodes where there is a friend, right? So let's say all these nodes are red, and let's look at an arbitrary node. Let's say node 7 in this first tree. So how can we actually check whether we can reach 7? Well, what we have to do here is that we can simply find which is the nearest node which is red to 7. And here we can see that the nearest nearest red node to 7 is 5, and the friend which is at node 5 will take 2 seconds to move from 5 to 7. And if we start from root, what we are going to do is we are going to take just 1 second to reach from 1 to 7. So that means we can safely reach 7 without getting caught. And it turns out that this is the method we can do, and we can similarly check for all the nodes. So the check is really simple. If time required, so another thing is that the time is nothing but the distance, because all of them are moving with the speed of 1 edge per second. So we can easily say that the time is nothing but the distance, right? So if distance of a node, so if distance of node from root is less than, so this distance has to be strictly less than distance of node from its nearest red node in its subtree. So from the nearest red node in its subtree, then that node is reachable. I have already proved why this is happening. So you might argue that why we are only taking nodes which are in the subtree of 7, and that's because if there is a red node in which is not in the subtree of 7, and that node can be reached to 7 before 1 can be reached to 7, then we don't even have to look at 7. We will just break out of the loop and in an ancestor of 7 itself. So that is the reason I am not looking at any node which is not in the subtree of 7, because if there is a node which is not in the subtree of 7 and it is getting reached by it is reaching 7 earlier than the root is reaching 7, then I will just break out of the loop before even I reach 7. So I don't need to look at that, because I am checking to 7 by assuming that I have been able to reach all the nodes which are above 7. So if there is a node which is not in the subtree of 7, then I don't need to consider that. So there is no need to get confused on that part. Okay, so I have successfully found a way to check for all the nodes what is the condition that the particular node is reachable or not. Now the question arises, how do we actually check this? Well, if you have some experience with solving problems with respect to trees, then it is not difficult to see how we can solve this. First of all, distance of any node from root can be easily calculated with a DFS, and it turns out that the distance of a nearest red node in the subtree can also be very easily calculated using DFS. I will show you guys the code. It's not something very difficult. You can just do a simple DFS and pre-calculate all the distances and the distance from the node to its nearest red node. So once you have that, what you can do is you can simply check if for a node, if the distance of its nearest red node is strictly greater than the distance of it from the root. If that is the case, then you can successfully reach that node. And if that particular node is a leaf, then the answer is always going to be yes. Then the answer to E1 is going to be yes. Okay. Now with this much clear, what about E2? How will we check what is the minimum number of people that we want in the grid to make sure that Vlad always loses the game? Well, it's not very different from E1, right? So if we encounter a node U such that distance of U from root is actually greater than the distance from the nearest red node, then obviously I have a friend in the subtree of U, right? And that friend is essential for me because that is the friend which is actually stopping me from going beyond U. And that is the friend which is stopping me from reaching U, right? And I have to take that friend because that friend is essential for me to stop. And once I take that friend, I no longer need to explore anything in the subtree of U because I really can't go deeper than U, since if I come to U, I will get caught. So if I have this situation that distance of U is greater than the distance of its nearest red node, then I know that I have a red node in the subtree of U, and that red node is essential for me. That is, I have to keep it. So I will keep it in the minimum subset that I want as an answer for E2. So it's very simple. Whenever I come to this situation, I will just increment my answer, and finally I will have my correct answer. I hope I am trying to explain it. I hope I am trying to give a better idea what's happening here, and it is getting clear. So I'll reiterate what I'm trying to say. So whenever I come to a situation where a distance of U is greater than the distance of its nearest red node, then I can't really reach U. And the reason I can't reach U is that there is a friend in the subtree of U which is stopping me. And that friend is essential for me to take. That is, in the problem, what they have asked me is that we need to find out the minimum number of friends that must remain in the maze, and that particular friend in the subtree of U must remain in the maze to stop me from reaching U, right? So whenever I encounter this situation, I will just increment my answer. And yeah, this completes the solution to both the problems E1 and E2, and I really fail to understand why people were able to solve E1 and not E2. But it is what it is. So that completes the solution. Let's have a look at the code now. Yeah, here is the code for E2. So first of all, what I'm doing is I'm doing a DFS to pre-calculate the distance and the nearest reds. So if the current node is not 1, then I do distance of current node is equals to 1 plus the distance of its parent. Pretty standard stuff. Also, if the current node is red, I am maintaining a Boolean array is red, which I am filling in the beginning. For all the red nodes, I am doing is red of x is equals to true. So if the current node is red, then the distance of its nearest red node is obviously going to be 0. Otherwise, it's going to be minimum of 1 plus the nearest red of all the nodes in its subtree. And this is what I'm doing. So yeah. Using this DFS, you can easily calculate the distance values and the nearest red values. And once you have done that, what you have to do is you have to do another DFS to check whether all the conditions are getting satisfied or not, right? So if I successfully reach a leaf node, that is current node is not equals to 1 and its adjacency list has a size of 1, that just means it's a leaf node, then I have actually ended the game and Vlad has successfully won the game. So OK will be true there. Otherwise, if it's not a leaf node, what I do is I check for the condition whether the nearest red node of x is greater than the distance of x or not. If that is the case, then I can successfully go to x. So I will just do a DFS to x. But if I can't go to x, then I will simply increment my answer because I know that there is a friend in the subtree of x which is essential for me to keep, which must remain in the maze, and so I have to keep it. So I increment my answer. And once I'm done with both the DFSs, I will just output my answer and get done, right? So yeah, this completes the solution to problem E2. It's not very difficult, and it's definitely not a 2000. I don't know how people are approaching E1 and E2 differently. They are essentially the same problem. Okay, that's it for problem E. Now let's move to problem F, and this is a very standard problem, but the solution that I have for this problem is actually very different from most of the solutions, and it is a very useful trick which I'm going to tell you in this problem. So yeah, stay tuned for this one. So this trick that I'll be telling in this problem is actually very useful in competitive programming, and a lot of people don't actually use it. So yeah, the problem statement again is involved, but exactly what the problem statement is trying to say is something like this. So we have an array and we have a number s. And what we have to do is we have to find the length of the longest contiguous subsequence of the array such that s plus the sum of all the elements in the array is positive. I mean, it's non-negative. Let me write it down. Okay, problem F. So we need to find the length of we need to find the endpoints actually. We need to find the endpoints of the largest contiguous subarray such that S plus sum of elements in the subarray is greater than or equal to 0. This is the entire problem at hand. And the trick here is that the elements can be negative, and that's why the problem is not very easy. Right? So the elements in the array can be negative as well. So yeah, we can't just simply create a prefix sum array and try to do some binary search on that array, because the prefix sum array itself will not be sorted because the elements can be negative as well. Now, for those who are experienced in competitive programming and know about some advanced data structures, the problem becomes really easy. There is a very straightforward n log square n solution which involves binary search plus segment tree or binary search plus Fenwick tree, and that solution can be reduced to O of n log n using n log n preprocessing with sparse table. But even then, the constant factor in the sparse table is quite large, so it's not a very ideal solution to do. But the solution that I am going to discuss right now is a pure n log n solution with almost no constant factor. What I'm going to do is I'm going to do a simple binary search as if I had a sorted prefix sum array, even though I don't have a sorted array. So the problem that we are facing is that the prefix sum array is not sorted. Now, what to do? Okay, so first of all, I'm going to iterate on the starting point. So if I am starting at an element I and I'm ending at an element j, then what I want is s. So this is the requirement, s plus sum of all the elements in the array I to j, which is nothing but prefix sum of j. I hope everyone knows what prefix sum array is. So what I want is prefix sum of j minus prefix sum of I minus 1 to be greater than or equal to 0. But I'm looking for the first index j where this condition breaks, right? So if this is the first index j where this condition breaks, if I'm starting at an element, if I'm starting at the index I, then the array from I to j minus 1 is a valid array, right? So for the first j such that s plus prefix sum of j minus prefix sum of I minus 1 is less than 0, the valid subarray will be from I to j minus 1, right? So essentially, for every I, we need to find the first j such that prefix sum of j is strictly less than prefix sum of I minus 1 minus s, right? And we know that if somehow we get the prefix sum array to be sorted, then this can be easily done using binary search. This is very obvious. If we have a sorted array, we can obviously very easily find the first index where the element is less than a particular value. That is nothing but a reverse lower bound type of thing. So we can very easily do that. But the problem for us is that the prefix sum array is not sorted, and that's really sad. But what we have is we have a trick, and using this trick I will simply convert the prefix sum array into a sorted array, and let's see how I'm doing that. So to do that, I will make a very important observation, which is that if prefix sum of I is greater than prefix sum of I minus 1, then prefix sum of I is useless. I mean, let me keep j for clarity. So let's say I am starting from an index I and I am looking for an endpoint j. And if I encounter a situation where prefix sum of j is greater than prefix sum of j minus 1, then prefix sum of j is useless. And that's simply because if this requirement is not satisfied for j minus 1, that is, if prefix sum of j minus 1 is not less than prefix sum of I minus s, and prefix sum of j is greater than prefix sum of j minus 1, then obviously prefix sum of j will still be smaller than prefix sum of I minus 1 minus s, right? So what I'm trying to say is, if p sum of j minus 1 is greater than equals to p sum of I minus 1 plus 1, and p sum of j is greater than p sum of j minus 1, then it implies that even for j the condition will hold that prefix sum of j is greater than equals to prefix sum of I minus 1 plus 1. But this is not what I want. What I want is this. And if prefix sum of j is greater than prefix sum of j minus 1 and the condition is not being satisfied for j minus 1, then obviously the condition will not be satisfied with j as well. So the observation is true, that is, if prefix sum of j is greater than prefix sum of j minus 1, then prefix sum of j is useless. So what I will do is, if I find a situation where p sum of j is greater than p sum of j minus 1, then I can simply replace p sum of j by p sum of j minus 1. And this is something that I can actually do here. And it is the trick which I was talking about. And magically, now the entire prefix sum array is sorted. Because for all the points where the prefix sum of j minus 1 was smaller than prefix sum of j, I have done prefix sum of j minus 1 equals to prefix sum of j equals to prefix sum of j minus 1. So now I have I have an array which is sorted in decreasing order. So yeah, magically I have converted this problem from unsorted array to a sorted array, and that is because of this simple observation that if an element is greater, if the prefix sum of an index is greater than those of its previous index, then that particular index is useless for me, because if the condition is not being satisfied for j minus 1 and prefix sum of j is greater than prefix sum of j minus 1, then prefix sum of j is a useless term for me. So I can just replace it with prefix sum of j minus 1, and now I don't have any index j for which p of j is greater than p of j minus 1, and so for sure I have an array which is sorted in non-increasing order or descending order. And now I have a sorted array, so now I can easily do a binary search and find out the first index, which is smaller than prefix sum of I minus 1 minus s. So yeah, this is the trick for this problem. We can convert it from an unsorted array to a sorted array and then do a binary search. So that's going to bring down the time complexity from O of n log square n using segment tree to a simple O of n log n solution. Okay, so this completes the solution. Let's just have a look at how exactly I'm implementing this. So first of all, I take in the array, I create the prefix sum array in the usual manner, and then this p sum 2 is the modified prefix sum array which is always sorted in non-increasing order. So p sum 2 of 1 will just be p sum of 1, but for all the elements from 2 to n, what I notice is that if prefix sum of I is greater than prefix sum 2 of I minus 1, then I'm just replacing prefix sum 2 of I as prefix sum 2 of I minus 1 in order to keep the array sorted in non-increasing order. But if that's not the case, then I'm just doing p sum 2 of I is equals to p sum of I. And now magically this p sum 2 of I is a sorted array. And then what I can do is, uh, for all the elements of the array, I can iterate for them being starting points. And obviously, if s plus a of I is itself less than 0, then it makes no sense to take that into account. Otherwise, if p sum 2 of n is greater than p sum of I minus 1 minus s, then that means that there is no index where this value is becoming negative. So high will just be n plus 1. Otherwise, I'm doing a binary search, and this is a very standard binary search. And using this binary search, I'm figuring out what the value of high can be. And here high is the first index where the value p sum of p sum of j minus p sum of I minus 1 plus s is becoming negative. And so my valid subarray is going to be from I to high minus 1. And if this and the number of terms will be high minus I. So if high minus I is greater than answer, then I will just do answer equals to high minus I, L equals to I, and R is equals to high minus 1. And if the answer is minus 1, I'm going to simply output that. Otherwise, I'm going to output L and R. So yeah, this is it. This completes the solution to problem F. And by this, I have completed the solutions to all the problems that were intended. So I'm not going to discuss anything else today. Thank you so much for watching, and I will see you in the next video. Bye bye.